Dear student, today I shall discuss the chapter Historical Development of Quantum Mechanics. The question is why quantum mechanics has developed. This is because in the later part of the 19th century, some of the experiments were reported that could not be explained by classical mechanics. That is, we called as failure of classical mechanics. So our first topic is failure of classical mechanics. That is failure of classical mechanics. Now, what are classical mechanics? Classical mechanics are Newtonian mechanics. These Newton mechanics or classical mechanics could not explain the certain experiment were reported in the later part of the 19th century. Now, what are the experiments? Number one is spectral spectral distribution of energy in the black body radiation. Spectral distribution of energy means how energy is distributed in different wavelength in the black body radiation that cannot be explained by our classical mechanics. Second experiment, photoelectric effect. Photoelectric effect and Compton effect. These two effects also could not be explained by classical mechanics. Number third one, variation of heat capacities by monoatomic solid with temperature. This experiment also could not be explained by classical mechanics. Number four, discrete spectra of atoms. That is atomic spectra. That also could not be explained by classical mechanics. Since the classical mechanics could not explain these experiments, that's why quantum mechanics has developed. Now, we shall see how classical mechanics is failed to explain these experiments one by one. The first definite failure was found in the study of blackbody radiation. That is spectral distribution of energy in the blackbody radiation. Now, first question is, what is a blackbody? What is a blackbody? A body which absorbs all the radiation that falls upon it. And also we know Kirchhoff's law says that black body are not only good absorber, but also they are also good emitters. That means blackbody can absorb radiation as well as blackbody can emit radiation also. Now, two scientists, Lummer and Pringsheim, they studied the blackbody radiation at different temperature. Now, what are blackbody radiations? That is, radiations are emitted by a blackbody are called blackbody radiations. Lummer and Pringsheim, they studied the blackbody radiation at different temperatures and obtained certain curves that are called experimental curves of blackbody radiations, and that curves are like this. In this line, this is lambda in atomic unit, and in this line energy, there is energy is a function of lambda watt per meter square, also it is atomic unit. So they studied the blackbody radiation at different temperature and obtain the curves like this. That is, first this is the lower temperatures, they obtain this curve. That is this is the say 3500 Kelvin. Next higher temperature increases and they got another curve like this, say 35400 Kelvin. In this the temperature increases and they obtain the curve like this. So this is a 4500 Kelvin and is 5000 Kelvin. So these are the experimental curves obtained by Lummer and Pringsheim on blackbody radiation. Now we shall discuss the interpretation of the experimental curves obtained by Lummer and Pringsheim. Interpretation of the curve. Interpretation of the curves. First interpretation, you see, as the temperature increases, energy for every wavelength, suppose this is the wavelength, energy for every wavelength also increases. So this wavelength at this temperature, this is the energy, at this temperature, this is the energy, wavelength is same. At this temperature, this is the energy, at this temperature, this is the energy. So as the temperature increases, energy for every wavelength also increases. This is the first observation. Second interpretation, see, as the lambda increases, energy also increases. I repeat, as the lambda increases, energy also increases and reaches to a maximum, and the wavelength corresponding to this energy and this wavelength corresponding to the maximum of the curve, maximum peak of the curve is called lambda max. So as the temperature increases, energy also increases, reaches to a maximum and then decreases further with the increase of lambda. This is the second observation. This is our lambda max. Another observation, number third, you see, as the temperature increases, lambda max, this is the lambda max for this graph, this is the lambda max for this curve, this is the lambda max. Now you see, as the temperature increases, lambda max shifts towards the shorter wavelength. I repeat, as the temperature increases, lambda max shifts towards the shorter wavelength. That is, lambda max is inversely proportional to the absolute temperature. That is, lambda max shifts displays towards the shorter wavelength. This is called Wien's displacement law. This is called Wien's displacement law. Why displacement? Because lambda max displaced. That's why displacement law. And the number fourth observation, the area, this area under the curve, this curve, at a particular temperature, the area under the curve at a particular temperature represents total energy of the radiation. And total energy of the radiation, E lambda, is directly proportional to the fourth power of the absolute temperature. This is called Stephen Boltzmann law. So these are the four interpretations of the curves. At that time, some theoretical attempt has been made to explain the curves on the basis of classical mechanics. So, one of the such attempt is given by Wien's, which is called Wien's contribution. Wien's, on the basis of classical electromagnetic theory of light, he derived an equation, and that equation is given by E lambda equal to A by lambda to the power 5 e to the power minus b by lambda t. So this is the Wien's contribution. See, in this equation, there is two parts. One is our normal one is the exponential one. We know exponential part is always more effective than normal one. So here lambda increases, energy decreases, but this part is more effective. So lambda increases, energy also increases. I repeat, lambda increases, energy also increases. That means lambda increases, energy also increases. That is, this Wien contribution can explain only this half portion of the curve. In other words, Wien's can explain the curve, half portion of the curve, and according to Wien's, the curve should be like this. That is, this Wien's cannot, or means could not explain the curve completely. Another contribution made by Rayleigh and Jeans, called Rayleigh-Jeans contribution. Rayleigh-Jeans contribution. So based on the classical equipartition of energy, Rayleigh engines, they derive an equation which is given by E lambda equal to 8 pi kt lambda to the power 4. So from this equation, we can see as the lambda increases, energy decreases. Lambda increases, energy decreases. So see that in the curve, lambda increases, energy decreases. Or we can say lambda decreases, energy increases. So lambda decreases, energy increases, and the curve should be like this. So again here, Rayleigh's contribution cannot explain the curve completely. It can explain only half portion of the curve. Once can explain this half, Rayleigh's can explain upper portions. Again, both the theory based on classical mechanics cannot explain the curve completely. It means classical mechanics is failed to explain the experimental curve obtained by Lummer and Pringsheim. This is the failure of classical mechanics, and of course this is the first failure of classical mechanics. Since the classical mechanics is failed, that's why quantum mechanics developed. 101, Max Planck's developed an hypothesis which is called Planck quantum hypothesis. Planck quantum hypothesis. So according to this quantum hypothesis, Planck quantum hypothesis, each atom of the black body behaves like a simple harmonic oscillator, and they have the characteristic frequency of oscillations, and these oscillators emits or absorb radiation discontinuously in the form of packets, in the form of energy packets. These are called quanta. So this idea is the revolutionary idea given by Max Planck. Energy of each quantum is given by E equal to h nu, where nu is the frequency of that radiation and h is the Planck's constant. And this is number 1 point. Second, the energy of nth level is the integral multiple of a quantum. On the basis of this idea, based on this idea, Planck developed a formula which is called Planck's radiation formula. So he developed a formula which is called Planck's radiation formula. Planck's radiation formula, which is given by E lambda d lambda equal to 8 pi hc by lambda to the power 5, 1 by e to the power hc by lambda kt minus 1 d lambda. So this is the Planck's radiation formula in terms of wavelength. This is formulated on the basis of quantum hypothesis. So next we can derive Wien's contribution, and this Wien's formula and Rayleigh's contribution from these equations. So let us derive Wien's contribution and Rayleigh's contribution from the Planck's radiation formula. Number 1, Wien's contribution, derivation of Wien's contribution. So we know one can explain on the lower part, the lower part of the curve, that is at lower wavelength. So when at lower wavelength, at lower wavelength, see here, lambda is low, that means this value is also low. That's we can write SC much greater than lambda k t. SC much greater than lambda kt, one can be neglected. That means, that is e to the power SC by lambda kt minus 1 is equal to e to the power SC by lambda kt. Now, that is, now the formula becomes, see here, or from this we can write E lambda d lambda equal to 8 pi SC lambda to the power 5. So this is nothing but 1 by e to the power SC by lambda kt, or 8 pi SC lambda to the power 5 e to the power minus SC by lambda kt. Now you see 8 constant, pi constant, c constant, h constant, co constant, that is the whole thing is a constant. This is regarded as a. Here s constant, c constant, k also constant. There is this quantity is also a constant. So we can write ultimately a by lambda to the power 5 e to the power minus b lambda t. So which is nothing but one's contribution. That is, we can derive one contribution from the Planck's radiation formula. That is Planck's contribution. That is Planck's radiation formula can explain the curve in the lower portion. Number 2, derivation of Rayleigh's contribution from Planck's radiation formula. So we know that Planck's radiation formula E lambda d lambda equal to 8 pi SC by lambda to the power 5 1 by e to the power SC by lambda kt minus 1. So you know, Rayleigh's can explain the curve in the upper part, that is at higher wavelength. So at higher wavelength, now this is higher, so this quantity cannot be neglected. That means at a higher wavelength, e to the power SC by lambda kt, only this portion is equal to expansion karo 1 plus s by mathematics, we can expand lambda kt plus 1 by factorial 2 SC by lambda kt square equal to 1 plus SC by lambda kt, ignoring higher term, ignoring the higher term. So this becomes this is. So there is this become this is. So from this equation we can write E lambda equal to 8 pi hc by lambda to the power 5 1 by directly this portion is nothing but this portion, that is we can write 1 plus hc by lambda kt minus 1. So 1 cancel, equal to 8 pi hc by lambda to the power 5 1 by, now directly this will go upper part, lambda kt by hc cancel, 1 lambda cancel, ultimately it becomes, ultimately is equal to, we can write 8 pi kt lambda to the power 4, which is relay J contribution. That is, now you see, from the Planck's radiation formula, we can derive both Wien's contribution as well as relay J contribution. That means Planck's radiation formula can explain the experimental curve both at lower part as well as upper part. That is, it can explain the experimental curve totally, completely. This is the success of Planck's quantum theory. From here, quantum mechanics has developed. I think you have understood clearly how classical mechanics fails, how quantum mechanics is able to explain the blackbody radiations. Thank you for watching this video.